Welcome to this Hobbs AP Chemistry class. Subscribe. Okay. All right. Couple of concepts today just for us to deal with. The first one we're going to talk about is this thing called resonance. I think in the other class I'm doing a better job with the outline. This would be, I think, letter H. Okay? Or bullet point, whatever one you're on.
Or overlapping orders.
It doesn't matter.
This is all under covalent bonding. Each one of those is a bullet point. Polar bonds is under covalent bonding. Okay? So this is another concept under covalent bonding. Resonance. A unique formation of a multiple overlap of p orbitals forming large pi bonds where, I'm loving my run-on sentences here, where the pi electrons get delocalized within the molecule. Now we look on our sheet and we see SO3. When we draw the Lewis dot structure for SO3, we draw it like this. And we have our 24 electrons in SO3. So now when we go and we want to figure out, okay, well, sulfur doesn't have its 8 electrons. It doesn't have its filled octet. So what do? We double bond. But the key is that we pick any two. We could pick these electrons here, or we could just as easily have picked those electrons on that one and made it look like this, or we could have picked the electrons over there and drawn the Lewis dot structure like this. So we get 3 equivalent Lewis dot structures. Now the reality is that the actual molecule is a hybrid of all 3 of these. So what's the shape going to be? What's our AX formula around this, and what's the shape going to be? Trigonal planar. What does planar mean? It's flat. Okay? So it's a trigonal planar molecule. It's a flat molecule. So each of these, what makes this unique is in our flat molecule here, in the SO3, now I got to do a different one. Oh, I got a mess up here. That's not the one I want. Come on, where is it? Where? Here it is. Okay. All right, so here, look. All right, come on. So in our SO3 molecule, we have a trigonal planar, our flat molecule. So here's your sulfur and your 3 oxygens. Now, each of these, if we look at the electrons, each of these actually is going to have an unpaired electron. Sulfur is going to have the electrons, everything that can form that pi bond. So we end up having these p orbitals that are all perpendicular to the plane. And you have your electrons in them, and all the p orbitals can actually end up overlapping. And instead of having a side-to-side overlap of just 2 p orbitals, we have a side-to-side overlap of 4 p orbitals. So we get this large pi bond. And what happens is the electrons then, when you have this, the electrons actually get delocalized where they're no longer held but just between these 2 atoms. Now they're in the whole molecule. Now remember, a p orbital has the lobe above and actually the lobe below. So we end up getting the layer of pi electrons above and a layer of pi electrons below. Now that's making the one big pi bond. So instead of the pi bond being between any 2 atoms, it's actually shared equally by all. So when we say the bond strength, the bond order, the bond strength is actually going to be less than a double bond, because this double bond actually is technically like being shared between all 3 of the oxygens.
So that only happens for trigonal planar?
Generally, it only happens for trigonal planar or linear. Okay? When you can draw equivalent Lewis dot structures, when the double bond can be in any one of the 2 or 3 different places, then we're going to have resonance. I'm going to show you a bunch of examples. So what we say now is that all three of the S to O bonds are identical. We don't have 1 double and 2 single bonds. We have all 3 bonds are now going to be considered to be identical when resonance occurs. And all are about 1 1/3 bond strength, bond order, which we call the bond strength. Now 1 1/3. That means it's stronger than a single bond, but not as strong as a double bond. The bond order for a single bond is 1. The bond order for a double bond is 2. The bond order for a triple bond would be 3. When we have resonance, since this double bond is said to kind of be shared between 3 spots, they all have the sigma bond, so they all have at least 1 in terms of the bond order, the strength of 1, but then they get about 1/3 more from the double bond, the pi bond. Now resonance, and you want to probably add this in, resonance adds stability to a molecule. Resonance adds stability to a molecule. Those delocalized electrons make the double bond not really want to be broken as much. So if we look at NO2, it's going to have to be NO2 minus. NO2 minus. This has 5 plus 12, 17, 18 electrons. So the nitrogen, oxygen, oxygen, 2, 4, 6, 8, 10, 12, 14, 16, 18. Again, it's NO2 minus. So now what's the deal? How would we finish the Lewis dot structure? We have to have brackets, but is the nitrogen have the filled octet? So we need to form a double bond, right? So pick 2, any 2. Does it matter which side I pick from? So I can have this, or, and when you have resonance, you do the double arrow, or I could have this.
So the correct Lewis dot structure is all 3 for SO2?
Yeah, it's really going to be the actual molecule is going to be something in between this. So what would you think the bond strength of each nitrogen to oxygen bond is going to be? 1.5. Both bonds are going to be identical. You're not going to have a single bond and a double bond. You're not going to be able to tell the difference between the nitrogen bonded to either oxygen. They're going to be identical in strength and characteristic.
Are there still lone pairs on nitrogen?
There are still lone pair on the nitrogen, yes, I forgot. Okay? So the shape is still going to be, it's going to be a bent molecule, but each oxygen, nitrogen, and oxygen all are going to have a p orbital perpendicular, and all 3 p orbitals are going to overlap. And those pi electrons then can go anywhere above and below in the molecule. So anytime you can put that, so we can have NO3 minus. NO3 minus has 18 electrons. Pardon me, it's going to have more than that. It's going to have 18. It's going to have 24 electrons. So we do the same thing. Nitrogen, oxygen, oxygen, oxygen. Put your 24 electrons. Okay? So there's 24 electrons. So again, nitrogen now is electron deficient. So what do? Form a double bond. Now again, which one can we pull from? All of them. So as soon as you can do that, and if you have a choice on where you pull electrons from, that means you're going to have the possibility of resonance. So what would so I can make it here. So what would my next resonance structure look like? On the top. Notice I'm only moving the position of the double bond. All the atoms, everything stays the same. Or we can go.
Double bond on the right.
Thank you.
So we have to write all 3.
Yes. On this past year's AP test, they actually gave a question, but they said draw. Let me actually look at it. All right, did anybody see my remote? Never mind. Did anybody hear it? Yep. Okay, this is the free response question on last year's AP test. My students, I don't think, did very well on this last year. And so we're going to do better this year. Passed it?
Or got, passed.
A bunch passed it. Most passed it. Only 12 didn't, quote, get a 3 or better.
Okay, well,
But
we got a 5.
Yeah, now the 5s were very low, and there were only like 3 5s, and that's very rare.
How many people did you have?
40, I think.
You have a lot more this year, don't you?
No, wait a second, it might have only been 30-something last year.
You have a lot more this year.
Yeah, a lot more this year. Okay, so here's the question, E. The HCO3 minus ion has 3 carbon to oxygen bonds. 2 of the carbon to oxygen bonds have the same length, and the third carbon to oxygen bond is longer than the other 2. The hydrogen atom is bonded to one of the oxygen atoms. So they're telling you that hydrogen bonds to oxygen. In the box below, draw a Lewis electron dot diagram, or diagrams, that's another clue, for the HCl3 ion that is consistent with the given information. So if we have HCO3 minus, okay, what's the central atom going to be? Carbon. Okay? So we put our 3 oxygens around it, and on one of the oxygens, okay, you might want to be up here so you can see. Put the one. We can pick any oxygen and put the hydrogen on it. Now we have 1 plus 4 makes 5, plus 18 makes 23, plus 1, so we have 24 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So carbon, okay, we got another seat up here if we need to be able to see better. Yeah. Now, what do I have to do for the carbon? I have to form a double bond. Which oxygen do I pull it from? Either one, right? So what does that mean? You have resonance, because if we did this, would this bond be the same as that bond? No, right now, as a double bond and a single bond, would they be the same? Double bonds are shorter than single bonds. Okay? Yes, sir.
So why does it say it's longer? Like it says that the third carbon to oxygen bond is longer.
The third one, because that's a single bond.
Okay, so
Single bonds are longer than double bonds. Okay? So, if we have resonance, and then by the way, we put that in a bracket. If we have resonance, then we can put the double bond there, OH, here, like this. Now, the reality is that what do we know about this bond right here if there's resonance?
it's a different right?
They're identical, right? So these 2 bonds are going to be identical. What's the bond order going to be for these 2 bonds? How many places is this double bond getting shared? 2. So it's going to be 1.5. A 1.5 bond order is going to be shorter. It's stronger than a single bond, weaker than a double. So, but these 2 are going to be identical, but shorter than the single bond here. So these 2 are the identical bonds. This one is the one that's going to be longer because it's a single bond.
Can you not double bond on that oxygen?
This one?
Yeah.
No, because it's got the bond here with the hydrogen. It can't form the resonance here because the oxygen can only form 2 bonds.
Oh, okay.
Plus, it would then, if you formed a double bond here, then you're going to have too many electrons around everything.
But can you form it there and then just leave the hydrogen?
But again, resonance, the only thing that changes place is the bond. You don't change the orientation of the hydrogens.
So that's like, it doesn't need all of the bonds.
No, it's just anywhere. If we have 2 equivalent Lewis dot structures, we have the choice on where we're going to form the double bond, with this oxygen or this oxygen.
So there's more than one.
That's right. Okay? So another example, well actually when we go and look then, get your packet out of questions. Yes. Okay, and look at question number 4. I think it's on the second page. Question number 4. Question? All right, y'all, come on. Question number 4, Andrew says, the NO bonds in NO2 minus are equal in length, whereas they are unequal in HNO2. So if we draw the NO2 minus, we actually just drew that one, NO2 minus, it's going to look like this. Oh, nice offset oxygen. It's going to look like this and this with the lone pair here. Oh, just 2. So if it looks like this, what's my resonance structure going to look like? You can put the double bond on this oxygen, right? So as a result, with resonance, these 2 bonds are going to be identical, and what's the bond order going to be for them? 1.5. So they're going to be equal in length, and since it's an ion, we put it in a bracket. But what if we drew HNO2? And so HNO2, there's no negative. It's still going to be the same number. It's going to be 12 plus 5 is 17, 18 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Nitrogen's still deficient, but this time where's the only place we can pull the electrons from? From this one. So do we have resonance possible here? No resonance on this one. So what does that mean as far as the bond length, bond order, and all that in terms of the nitrogen-oxygen bond here versus here? This one's going to be shorter, higher bond energy, stronger than that one. So in other words, you're going to have 2 identical bonds here because of resonance. Here, you're going to have a double and a single bond. No resonance because of the presence of that hydrogen. Just like on that HCO3 minus, that third oxygen couldn't be part of the resonance structures because of the presence of the hydrogen.
Is the ratio 2 to 1 for double to single and 3 to 1 for triple?
No. As far as length and all that and strength, no. Okay? So resonance is always when you have multiple overlaps. Now the most common, most important resonance structure is that of benzene. What's benzene's formula?
Is it like C6?
Benzene. C6H6. It's a... All right, come on, y'all. So, carbon, and it has a hydrogen onto each one. But each carbon now has 3 bonds. It has 1 bond left over. So when you do this, you end up having alternating double bonds. But we could just as easily we put our hydrogens here. We could just as easily put the double bond here, here, and here. So what do you think the bond order is between each carbon to carbon?
1.5.
Why, Reese?
Well, because you've got, for each carbon there's a 2 and a 1.
It's kind of like now resonance implies if you talk about like the noise resonating down the hallway, it makes you think that it's like bouncing back and forth off the walls, resonating off the canyon walls for an echo. So the term resonance implies, and it's not really true, that the double bond is kind of flipping back and forth. And so that's not what it's doing. It's a sharing of the electrons. But You can think of it as this double bond being shared between these 2 points. This double bond between these 2 points, this double bond between here. Or you can think of 9 bonds in 6 places. So it's 9-6 or 1.5 is the bond strength. Now what happens is all the 6 carbons all have a p orbital perpendicular. So what's the AX formula around each carbon? AX3. So the shape around each carbon is trigonal planar. So once again, this is a totally flat molecule. Actually 12 atoms are in the same plane. Totally flat molecule. But each carbon has a p orbital that's perpendicular to that plane. And I had a picture of it.
How does p orbitals get perpendicular?
This just when they go to hybridize. When they hybridize, one of the p orbitals stays unchanged.
Okay.
Now again, how does it know? I don't know. So if we look at the carbon atom, here's your hexagon ring. Okay? Here's the hexagon ring. Got to get over here. So these are all your sigma type bonds. This is your 3. What type of hybridization is AX3 going to be? Okay, somebody on the front row. What type of hybridization is AX3 going to be? SP2. S plus 2 P's add up to 3. AX3. So this is SP2, trigonal planar. But then each one of these is going to have a p orbital that's perpendicular to it. And it's going to make it, here are your p orbitals. So your carbons, and it's kind of showing then you get this cloud of pi electrons. Here are your p orbitals on each carbon atom perpendicular to the plane. And they're all going to overlap one another. And so we end up getting this ring, or this cloud of pi electrons above the plane and below the plane. So when we draw, now I need to put this back on. And I'm about to run out of battery on this thing. When we draw this, a lot of times we'll draw it like this, which is going to imply the resonance that the double bond is shared equally by all. So that's what the ring, so this is our benzene ring, so we assume there's a carbon at each vertex, and the ring is implying the resonance of the combination, the hybrid of these 2 structures.
So we could just draw that and that would be the same.
This is the same thing, but when they want the resonance structures, you have to draw it out like this. But this is the way most people draw a benzene molecule, like this, and the ring implies the resonance.
So the diagram that you showed, like before this one with the balloon-shaped stuff, there's like no difference between the single and double bonds in that one?
That's exactly right. That's the sigma part of the bond, and then they all share the double bond. The pi electrons are all shared equally.
And that's not in that diagram?
Well, the first one was showing just the sigma bonds, the first bond. So they're all going to have that. That's why we say the bond order is 1.5. They all have the sigma 1. But then the pi bond then is equally shared. So there are another 6 electrons that just kind of hover above and below the plane, and they just get shared equally by all. And that's the 0.5 part of the bond. That adds the extra strength. Now, what's unique about this is that normally, if we go and react this with, say, chlorine, the chlorine would go and break the double bond and put chlorines onto each of the carbons if it was just a normal double bonded carbon to carbon. But because of resonance, rather than doing what would be called an addition reaction, where we add the chlorine, break the double bond, add the chlorines, instead, we're going to get a substitution reaction where the chlorine's just going to come in and it's going to keep the double bond. because it wants to keep the resonance. It wants to keep the alternating double bonds present. That's when we say that the resonance adds stability to the molecule. So how the molecule reacts changes because of the ability to have these resonance structures. Because of those pi electrons being delocalized and shared, it adds stability to the molecule. So anytime you have multiple possibilities for drawing Lewis dot structures, you're going to have resonance. And then the bonds, wherever the bonds are being shared, those bonds are going to be equivalent. And it's either going to be 1.5 in terms of your bond order or 1.3 if it's shared between 2 places or 3 places. It's never going to be more than that. All right? That's the first concept. Everybody, any questions on that? And we'll do some practice. We'll do some practice with that. Second concept. Last concept. Yep. Next bullet point. Formal charge. Okay, Anthony. Formal charge. This is just a different way of trying to decide what's the best Lewis dot structure. Because when we do oxidation states, it implies that electrons are lost and gained. When we say sulfur is in a +6 oxidation state, you think that it's lost 6, that it really has a +6, and it's really not accurate. Formal charge gets a little bit more accurate as far as what's really going on with electrons, gives us an alternate way. So it's really just going to be nothing more than plugging into the formula of valence electrons minus 1/2 of the bonding electrons minus the number of lone pair electrons. And this is actually the total number of electrons, not just pairs. Okay? So this is our formula to get the formal charge. Okay? Atoms want the lowest possible formal charge when bonding.
Why is that formula?
This is just the formula that they came up with, whoever they are, just because. They said so. All right? So, if I look at even a simple compound like water, H2O, it's going to bond like this. So I want the formal charge on the oxygen, and I need the formal charge on the hydrogen. So the oxygen's formal charge, how many valence electrons does oxygen have? 6, right? Minus, how many of oxygen's electrons, how many bonding electrons are there? 2, 4. So oxygen gets credit for half of them. So it's 1/2 times 4. Minus, how many lone pair electrons are there? 4. There's 2 pairs, but 4 electrons. So it's going to be minus 4. So it's 6 minus 2 minus 4. That's going to equal 0, which is ideal. That's what you want. You want the formal charge always to be 0 because this is a covalent compound. It doesn't have a charge. Hydrogens, it has 2 valence electrons minus 1/2 times 4 minus 0 valence electrons. So again, it equals 0. So we have optimized, with this dot structure, we've optimized the formal charge. Does everybody know where the numbers are coming from? That's what we want. You always want to make your molecule so the formal charge is equal to 0. Now let's look at a situation where it's maybe not quite so clear. Anthony. 2, 4. It's bonding electrons. Okay? So, let's look at another molecule. H2SO4. Okay? H2SO4, stay with me. If I have sulfur, I put my 4 oxygens around it, and then I put my hydrogens right here. I satisfy everything. As you do all your electrons, you satisfy everything. This is the way we would do H2SO4 in terms of the octet rule. Everything satisfied all, everything has 8, y'all listen, everything has 8 electrons around the central atom. This would be, unless they specifically say, you know, what is the Lewis dot structure in terms of best lowest formal charge, you would just draw H2SO4 like this. But in terms of formal charge, we want to look at the formal charge of the hydrogen, the sulfur, and the oxygen here. Well, the hydrogen is going to be, we have 2 of them, so the total number of valence electrons is 2 minus 1/2. Again, you're going to have, for hydrogen, it's got 4 bonding electrons. So 1/2 of 4, and the hydrogen never has any electrons, so hydrogen is at 0. That's all good. But now we have 2 different oxygens. We have oxygens that are bonded to hydrogens, and we have oxygens that are just by themselves. So we have oxygen 1, oxygen 2. So we have 6 minus, well this one, these will be our 1s, these will be our 2s. This one is got 4 electrons involved in bonding, so it's 1/2 times 4 minus 4 electrons. So once again, we're at 0. That's a good deal. But oxygen 2 has 6 valence electrons, but only 1/2 of 2 minus 6 valence electrons. Lone pair electrons. So that's going to come out to equal -1 for both of them. And sulfur has 6 valence electrons, minus 1/2 of 8 minus 0, it comes out to -2, or pardon me, plus 2. Now what we want to do is we want to minimize formal charge. So to do that again, you steal from the rich and share with the poor. You take from the negative and add them to the positive by forming double bonds. So each oxygen is -1. The sulfur is +2, which means then that I would form a double bond there, and I would form a double bond there. So now that's going to make the formal charge, it's going to be 6 minus 1/2 of 12 minus 0 is going to equal 0. This is going to be 6 minus 1/2 of 4 minus 4 is going to equal 0. Because you have 2, 4, 6, 8, 10, 12. Because you're forming the double bond now, that's going to be another pair of electrons.
Where'd you get 6?
That's the number of valence electrons that sulfur and oxygen each have. That's group number.
What about hydrogen? Why is hydrogen 2?
Because we have 2 of them. We're just...
Why not do 12 for the oxygen?
That's a good question.
I mean, if you do 1 hydrogen...
Okay. Well, I was just doing them all together. If you just did hydrogen, that's probably a better way to do it, and I don't know why I was doing it that way. So if we did hydrogen, just did 1 minus 1/2 of 2 minus 0, it's going to come out to the same thing. I just did them both together. Okay? Now, technically, you could have done the 2 oxygens that are the same together. Is that what you just figured out? Yeah. Okay? Now, I'm missing out on something back there. Okay, so we want to minimize formal charge. Now, how, this is an obvious expanded octet. How does the bonding occur? What's the shape? That's way beyond the scope of any of our discussion here. Okay? So, I mean, you use, in terms of formal charge, you leave it like this and you won't have to worry about shape or anything. So when we want to minimize formal charge, you just have to go and you find out what the formal charge is based upon your normal Lewis dot structure, Then if one is positive and one is negative, you steal from the rich, share with the poor, form your double bonds, and then we can have your minimized formal charge. So, what I want you to do now is I want you to go through on that sheet, and on the back of that sheet, I want you to redraw each one of those 15, okay? Calculate the formal charge for each element, and then minimize the formal charge. All 15 of them.
Am I going to be able to do my test
Y'all, it's not going to take that long. Hey, listen, you already have the Lewis dot structure. So you just have to recopy that, calculate your formal charge, and then if you need to, redraw it, minimizing formal charge. Luckily, it fell on my foot and stopped from hitting the ground.
Wait, what?
That was the hydrogen spectrum tube. That's this.
Oh, that. Yeah.